Okay, next we're going to go over question 3, which I've copy pasted over here. I've also copy pasted the instructions to save some time. So let's first quickly go over what the question is asking. Again, we're asked to prove if the language is regular or not. If it's regular, we make a DFA for it /NFA. If it's not regular, we use a pumping lemma to prove that. So let's go over what the language is. So the language is all strings over alphabet A, B, C, where the string is in this form. So A to the X, followed by B to the Y, followed by C to the Z. So this just means there's X, A's at the start, followed by Y, B's, followed by Z, C's, where X is greater than Y and Y is greater than Z. So in other words, the strings are all in the form where you have more A's than B's at the start, and then more B's than C's. So for instance, this would be in the language. Because we have 3 A's, which is more than 2 B's, then we have 2 B's, which is more than 1 C. But then this would not be in the language, because we have 3 A's followed by 3 B's, and 3 is not greater than 3. So let's move on to the proof now. The first thing to think about is whether or not this language is regular. So whether or not you could actually make a DFA for this. So if you think about it, you cannot actually make a DFA for this because you need to keep track of the number of A's you've seen in relation to the number of B's, and then the number of B's in relation to the number of C's. And this would require infinite memory or like infinite states. You could only do this with a PDA that has a stack, not a DFA, which is too simple to do this. So the language shouldn't be regular. We just need to prove it. So as always, we have this boilerplate. We assume towards contradiction that it's regular, and then write out all the properties. And our goal is to find a string in L with length at least n, and then show that there is no breakdown for which these 3 properties hold. So let's think about a string that we should choose. We want one where we can either pump down or up and take the string out of the language. Now the first thing to consider is that if we have a string where the first n characters are full of A's and then something like this, then by pumping this up, we would not be able to take the string out of the language because the language wants us to have more A's than anything else in the string. And so if we keep adding A's to the string, then we won't reach a contradiction. And remember that because the first 3 n characters are A's, the first n characters must also be A's, and therefore x and y can only contain A's. So pumping up would be kind of useless for this question. So we want to find a string where pumping down would take us out of the language. So let's think about how we could have that. If we have some characters at the start, and we're trying to go out of the language by pumping down, we essentially want to have a case where there is not more A's than B's. So the amount of A's is less than or equal to the amount of B's. And if you want to pump down and get this to be true, we want the amount of A's to be very close to the amount of B's before pumping down. So let's do that. We're going to set the amount of A's to be n plus 2, the amount of B's to be n plus 1, and the amount of C's to be n. So there's just one more A's than B's. So in your head, you can think that if we were to apply these properties, x, y would only contain A's, y would have at least one A, and by pumping downwards, we would be removing an A from the string, at least one A. And so we'd have that the number of A's would be less the number of B's, or less or equal to the number of B's, which is what we wanted to take the string out of the language. So let's try this. Let's try write it down for me. So we have that W is an element of the language, and that the length of W is going to be n plus 2 plus n plus 1 plus n, which is just 3n plus 3, which is greater than or equal to n. So because this is true, then by the pumping lemma, there must exist a breakdown. So therefore, there exists a breakdown W equals to xyz such that the three pumping lemma properties, sorry, it's a bit messy, hold. Now, as mentioned before, because of property 2, we know that xy consists only of a's. And then by property 1, because y is not empty, y contains at least one a because it's not empty. And so by pumping up, we would be adding a's, which doesn't help us. But by pumping down, we would be removing y, which contains at least one a. So we would be removing at least one a from this portion of the string. So let's do that. So by pumping down, x, y, 0, z would, so first let's define the amount of a's in y. So let k be the number of a's in y. So y equals to a to the k for some k greater than or equal to 1. And so x, y, 0, z would be this part, this string, with k less a's than before because we removed y, and y has k a's. So this will be a, then n plus 2 minus k, because that's how many a's removed. So n plus 2 minus k. The other parts of the string stay the same. Okay, and now because k is at least 1, we know that n plus 2 minus k is going to be less than or equal to n plus 1. So we had n plus 2, and we removed k, and k is at least 1. And so we know that this entire thing is definitely at most n plus 1. So the amount of a's at the start of x, y, 0, z is not greater than the amount of b's. Sorry for the handwriting, by the way. The amount of b's. Therefore, x, y, 0, z is not in the language, which contradicts this property. Contradicting property 3 of the pumping lemma. So therefore, by contradiction, our assumption that L was regular is wrong. So it's not regular. By contradiction, L is not regular. And that's it for this question. On to the next.